So we have obtained the expression for Q potential of the system, and now we will be deriving the thermodynamics of the system from the knowledge of the Q potential of the system. So we have the Q potential which we concluded in the previous lecture, that is Q is equal to PV by KT, or Q is equal to log of Z. Z is a grand partition function which was proved to be equal to PV by KT. So this is where we begin our just discussion. So we will obtain thermodynamic quantities one by one. So first we begin with the pressure, which is quite an easy job, okay, as it is directly in. So pressure, how do you get pressure? So you know that pressure is given by rearranging that above equation, which we named as equation number 6 in the previous lecture. So P is equal to, I can say just cross multiply that KT by V into Q, right? Or I can write also as KT by V into log of the grand partition function. So that gives you the pressure. Now we can get see all the thermodynamic quantities of interest, that average number of particles. So you know, in grand canonical ensemble the system, the number of particles is a variable, or the number of particles of the system will be fluctuating. So average number of particles, we can call that one as n bar, right? So what is n bar is equal to? N bar is nothing but the ensemble average of n, which is already we have seen that this is related to minus dou by dou alpha of log of Z. That's what we have seen, minus dou by dou alpha of log of Z. Now this minus dou by dou alpha can be proved to be equal to see in terms of the fugacity. Let's do that one just here. See, minus dou by dou alpha, I'm doing that one in terms of the fugacity. So that is dou by dou alpha. So you see, dou by dou alpha can be proved to be equal to minus Z. Z is the fugacity, note the grand partition function, dou by dou Z. So we can use this identity. I can remember either it is an identity or we can prove it. So let's see how to do that one. See, you know, to do this particular thing. Like so you have Z is equal to the fugacity, Z is equal to e raised to minus alpha, right? So that is equal to e raised to mu by KT. That is the definition for the fugacity, e raised to mu by KT. So therefore we can say that dou of Z by dou alpha, dou Z by dou alpha, that will be equal to, we can say minus e raised to minus alpha, right? Minus e raised to minus alpha. So dou Z by dou alpha will be minus e raised to minus alpha, dou alpha. So therefore, or thus we can write dou by dou alpha can be written as, if you want, dou by dou alpha can be written as dou by dou Z into dou Z by dou alpha. We can write like this, okay? Is it not? Now, which can be again written as is equal to dou Z. I'm just rearranging that one. Dou Z by dou alpha. I'm writing, I'm inverting the relation, which is permitted in partial derivatives, dou by dou Z. So I'm writing this as an operator equation. So that is equal to, and don't you know what is the dou Z by dou alpha from this relationship? That is equal to minus, that's equal to minus e raised to minus alpha into dou by dou Z, into dou by dou Z. And what is this e raised to minus alpha? Minus e raised to minus alpha is Z. Okay, so that is equal to minus Z into dou by dou Z. So that is our identity that we have used here, right? So dou by dou alpha can be written as what? Minus Z dou by dou Z. So I am rewriting this one. This is also equal to, so this factor can be minus dou by dou alpha is here. So minus dou by dou alpha will be equal to simply Z into dou by dou Z. So I'm writing this as Z. This is equal to Z dou by dou Z. Z dou by dou Z. Remember, here the small z is used, which is nothing but the fugacity. Okay, and here the capital Z or script letter Z denotes the grand partition function. Okay, now once again one more identity will be using. So this is equal to, we can use this is equal to KT times, we will just show that KT times dou by dou mu. there are some identities that we have used. Kt times dou by dou mu of log of z. So where we have used another identity. So let me call this one as, for the time being, this is equation number 7, relevant equation, and this is finally equation number 8, which gives you the average number of particles in the thing. So now here we are left with one more task, that we have to prove that dou by dou z, right? Z dou by dou z is equal to kt into dou by dou mu. We can do it in a similar fashion. See how do we do that? Let's see that. So dou z, let's see how to do that. Dou z is can be written as simply dou of e raised to z is e raised to mu by kt. Okay, I'm writing that one. So that is equal to 1 by kt, right? So if you take differential, 1 by kt e raised to mu by kt, into d mu. Okay, or I can write the other way, dou mu, partial derivative, you know. So you can write this one as dou mu into dou mu. So therefore what will be z into dou by dou z, I can write z is what, e raised to mu by kt into dou by dou z. Already we have obtained from this relation. Okay, so I'm substituting that in the denominator, that is 1 by kt. Okay, 1 by kt, I'm substituting 1 by kt e raised to mu by kt into dou mu, right? Into dou mu. So what will happen, this e raised to mu by kt will be getting cancelled. So what you are left with is what, that kt goes up, so that will be equal to kt dou by dou mu. Is not kt dou by dou mu. So that is what we had to we have used there. So instead of z dou by dou z, we can always use kt dou by dou mu, and instead of what, minus dou by dou alpha, we can use what, z dou by dou z. So it's what I advise is that you remember these two identities, or remember them as identities. What is that? First one is that minus dou by dou alpha is equal to z dou by dou z, which is further equal to, we can say, kt times dou by dou mu. So why do we use all these things? Because sometimes your expression will be a function of alpha, sometimes it will be a function of z, some other times it will be expressed as a function of chemical potential. So depending on how our right hand side, means the what you call partition function, z is expressed, whether it is expressed as a function of alpha or z or mu, you have to use what that corresponding partial derivatives accordingly. So that is why we are just making a change of that one. So anyway, equation number 8 or the previous steps also will be giving you the average number. Now same manner, let me go to the third quantity. So the third quantity, I can say third quantity, that's average energy. Okay, average energy of a system in grand canonical ensemble, average energy. Or we can say in a system where the energy is fluctuating, the average energy is taken as the internal energy. That's a representation of the internal energy of the system. So let me say that is E bar of the system. So here U equal to, we can say E bar, that is nothing but the ensemble average of the quantity E. And already we have seen that that is equal to, we have proved that that is equal to dou by dou beta of what, log z, from some equation number 12 or something in the previous derivations. So that is equal to dou by minus dou by, and hope you remember we are already familiar with an identity of dou by minus dou by dou beta. Minus dou by dou beta was proved to be equal to kt square dou by dou t. That already we have done in canonical ensemble derivation. So remember that identity as well. Okay. So with that will become is equal to minus is gone. So that is kt square dou by dou t of log of z. You can understand that why we do this one, because z, as we have seen, that z is usually written as a function of mu v and t, right? Mu v t. But we are taking dou by dou beta of z. So when you take dou by dou beta of z, usually the problem is that z is to be expressed in terms of beta. Beta is 1 by kt. So it's good, or it's easy to do the derivative if z is rather expressed as a function of what, t. That's why we are taking re-expressing the derivative in terms of dou by dou t. That's the thing. So now that is the thing. Remember, this is the expression for what you call the internal energy of the system, so which can call as equation number 9. So average energy of the system or internal energy of the system in grand canonical ensemble is equal to kT square dou by dou t of log of z. Remember the same expression we got for canonical ensemble as well. Okay, so here there also you got u is equal to minus dou by dou beta of, in place of z we wrote q. Okay, and finally we wrote this one as what, kT square dou by dou t of log q. That's all. Okay, so you can just see the similarity, close similarity between the thermodynamics in canonical and grand canonical ensembles. So now again moving on to the next statistical or thermodynamical quantity of interest, which is the fugacity. Okay, so the fugacity or chemical potential. From fugacity you can go to the chemical potential. Chemical potential is a significant quantity in system of grand canonical ensemble mu. So from fugacity z is equal to, we have fugacity z is equal to e raised to mu by kt. We are interested in the chemical potential of the system. Okay, therefore I can say, taking logarithm, or I can say mu by kt is equal to, you take logarithm, so then log z, right? So there is a log of small z. So don't get confused with the log of capital Z and log of small z, which will be appearing together. So or I can say, or what you can say, we will get see mu is equal to, on cross multiplying, kt times log of z. Mu is equal to kt times log of z. So that we call, that's done. So we need this equation later. Mu equal to kt log z. Okay, that is a relation for chemical potential and fugacity. Similarly, we can, if you want, you can just get some more things like, say, the Helmholtz free energy of the system. So the Helmholtz free energy. All these the quantities are thermodynamical quantities. Helmholtz free energy. A, right? A or F we usually use. You know that A is equal to mu n minus PV. A equal to mu n minus PV. So I can say n into mu is what, let's just now we have obtained mu is equal to kt log of fugacity, then minus kt PV equal to, right? Okay, PV equal to, you know, PV by kt we have proved for grand canonicals, that is equal to log of capital Z. So what will be PV equal to? PV can be written as what, kt log of Z. Any relevant equation will do. Okay, just it's a matter of, so what I can do is that it can be written as what, kt log of Z raised to n, right, on rearranging, minus what, kt log of capital Z. So we can take this one as a common, or rearrange this one, log a minus log b, and then you can take it as log a by b form. So finally you are getting a is equal to minus kt. Okay, or you can just use the other ones, log z by z raised to n. Okay, so that is what we are going to get. So this means that this is some equation number 11 to call. So now finally we can go back to entropy. We already had derived entropy, but we can go for still another expression for entropy, that is entropy of the system. All these are relevant thermodynamic quantities. It depends on what we are interested in. So entropy S equal to, you know, okay, U equal to A plus TS. U equal to A plus TS. So S will be equal to U minus A by T. S equal to U minus A by T. So which I can write as U by T minus A by T. It's a matter of rearrangement. So you have got an expression for both U and A with us. So I'm substituting for that. So that is equal to, further that's equal to, I'm writing it here. Let me write it. Yes, this is equal to U. What is U? We obtained U is equal to kt square. Okay, kt square dou by dou t of log of z, right? So divided by t I'm putting, minus just now we have obtained the previous equation, nkt, nobody the complete thing, can be anyway, you can write that nkt log z. It's not the final expression I'm writing, nkt log z plus kt log z, capital Z, divided by t. So t you can just cancel away everywhere. So here also t square, one of the t will be getting cancelled out. So what you are left with, so there are a number of ways of writing this one. You could have substitute equation number 11 also, but this is a standard way of equation that is usually found. That's why I'm using, okay, dou by dou t of log of z. Any other equivalent equation will do. okay, minus nk log z minus nk log z plus k log z. So that is also an expression. You need not memorize any of this equation. I just suggest you to memorize only the relevant equations, like what is Q potential, what is fugacity, what is the relation between average energy, okay, what is the expression for what do you say, n bar, e bar, etc. That is more than enough. Okay, so how to get it, and the rest of the thing you can do as per the need of the need of the situation. So that's about the derivation of thermodynamical quantities for a system in grand canonical ensemble. So before we end up the thing, so let me just summarize what all equations that we have obtained. So the summary of the thing is here. So the summary we started with the definition of Q potential. Okay, Q is equal to log of z. So from that we rearranged, we got PV by KT is equal to Q equal to log z. So from there we got the pressure is equal to KT by V into log of z. That's the second one. Second one, the average number of particles, because number of particles is fluctuating here, that was obtained as KT dou by dou mu of log z. It's always good that you summarize all the results that you got. Third one is the average energy, which is understood or regarded as the internal energy, that was KT square dou by dou t of log z. Just it's good that you compare it. Okay, fourth one, you got the chemical potential related to the fugacity as KT log small z. Small z is the fugacity. And the fifth one, we obtained the Helmholtz free energy of the system is equal to minus KT log of grand partition function divided by fugacity raised to n. And similarly, we got an expression for the entropy, that is a KT dou by dou t of log of z, the grand partition function, minus nk log of fugacity plus k log the grand partition. So these are the equations of interest for a system in grand canonical ensemble. Okay, so hope that the discussion was useful for you, and you can just refer for more expressions of this kind. Okay, thank you.